Okay, welcome back. I guess we'll go ahead and get started for this meeting. And looks like almost everyone is here, but we'll go ahead and get started. It's about 6:04. So let's see. So this. Okay. Okay. So the plan is still that we'll have this meeting tonight via WebEx, and then next Monday we'll be back to campus in the classroom that's indicated in the syllabus and in your Laverne portal. So yeah, so let's assume unless there's any new announcements, and I think the plan is starting next Monday, and I'll send an email, but we'll meet on campus in the scheduled classroom, which is this one, Landis Academic Center 101A, which I think is right next to the one we had last term. And so if you don't hear otherwise, next week I will see you there instead of via WebEx. So that'll be nice to get back on campus. Okay, and again, today's meeting will be recorded, or is being recorded, and I will post it to the little YouTube page I set up. And so I think everybody was able to access the video from last week, I think. So just one more reminder that, okay, if you go on Blackboard and you scroll down, I put a link here to the MDA504 YouTube page, and right now there's only one meeting or one video because we only had one lecture. But if you click on it, uh, this week's video and last week's video will be here. And I don't anticipate having more videos because we're going to be back on campus, but if there are, they'll be here. So everything from last week and this week you can find here. Where are we? Okay, so the first homework assignment that most of you already turned in is just a reminder that's due today. So, where's this? Here we go. Okay, so assignment number one that we did last week, that's due today or tonight by midnight. So if you haven't emailed me your documents for that, make sure you do that today. And I'll try to get the first homework assignment graded sometime this week, and then you can see your grades for that. All right. And today's lecture is going to continue here in the syllabus. So this is week 2, February 7th. We'll do a couple lecture slides. So we'll look at network initialization and stopping, and we'll look at parameter estimation and network optimization. And then we'll do some. Everyone's here. All right. And then we'll do some more examples with enterprise monitor. So let's. Um, okay. So any questions or anything from week one, or any questions or comments before we start the lecture for today? Okay. All right. Perfect. Okay, let's close this for now. Okay, we'll come back to that. All right, so the PowerPoint for today, I already have it open, but if you go to uh, where is it? Weekly module and week 2, you'll see the lecture slides for today here. So we'll start with that. Okay, so there's a lot of slides here. I'll try to do just to cover the basics and get an idea of what we're going to cover today in Enterprise Monitor and the material that you'll do some examples with, and then we'll reinforce the ideas with some videos in some readings that you'll do on your own time. Okay, so first thing let's talk about is network initialization and stopping. So we're trying to determine how you set up the network and how and when the stopping rule is. Like, does it go 5 iterations? Does it go till a certain point? Does it go till some criterion? And so there's different ways in which you can tell the network to stop building. Okay, and one of the things we need to have the software, the program, or the model do is determine if we're at a max. Like you're probably familiar from calculus and other analyses that if you take the derivative of some function, it tells you, and you find the point when it's zero. Um, that doesn't 100% tell you if you're at a maximum or a minimum. So you know that when the derivative of the slope is changing and it gets to zero, you're either at a minimum point or a maximum point, and you essentially want to find the maximum point. And so there's different ways you can avoid the fact that you might be at a minima instead of a maxima, and we'll see how to do that. So like the derivative at this minimum point and this minimum point and this maximum point are all zero, but you normally want to find the maximum point in some function, right? So there's ways we can set that up. Okay, so we're going to learn how to initialize a procedure with different input to hidden weight specifications. And there's normal, there's uniform, and there's this Cauchy mode. And these are different processes or models we can set up in Enterprise Miner. And we'll see how we can set up the network function with these different forms. Okay, and determine the weights of the inputs that lead to the outputs. Okay, so we'll start with some default or a small number, and you want to start at something like 5, and then you take a few training steps, like you go to 6 and see if the model improves. Uh, so you can basically go like a step-by-step situation where you go like one step, then another step, and if the model keeps improving, you keep going more steps. Or you can just set the number of steps by default, like 10. Say the model's going to go 10 times or 10 iterations, and then it stops. So there's different ways in which you can kind of tell the model to start and then stop based on some preset criterion or just go step by step. Okay, convergence criteria. And so there's conditions here in which the convergence is declared, depending on how you set it up. So number one is when the error function stops improving. So when your error isn't getting any, uh, isn't changing, you can stop because if your error function isn't changing, then continuing with the iterations isn't really doing much. Okay, so if the gradient has no slope, that means that a minimum or maximum has been reached, right? Then you can stop. Or if the magnitude of the parameters stops changing substantially, if so basically like if your error function is not changing anymore, if you're at a minimum or a maximum, or if like the parameter or coefficient estimates aren't changing, then either of those three conditions is one are ways in which you can stop the convergence. Okay, weight decay, and so you can use different weights uh, to specify your model. And weight decay is when you can kind of start with a certain weight and then have it gradually minimized to keep the weights from growing too large. And you can do that by looking at the sum of the squared weights, and that'll tell you when your objective function for the weights is the best. Okay, another way to set up a network and then stop it is just to have an early stopping rule. And so we've done this, we can split the data set into training and validation. So maybe 10% is for validation, the other 90% is for uh, training. Okay, and then you can say like the network stops at this point and see how it works in the training, the validation purpose, then use it on the training. Okay. Then you want to choose a network architecture, which we're going to look at in Enterprise Miner. Um, you'll start with parameter estimates that are close to zero and start adding them in. And then you can train your neural network to kind of learn from the way it's set up. And then based on how it performs in the training set, it can make conclusions in the rest of the data. Okay, and you want to select the parameter estimate that has the best performance on the validation data that you're validating the model with. Okay. Okay, so early stopping and network initialization. Okay, and we're going to look at learning and how parameters are estimated by um, the learning function getting set up. Okay, so you know that your true parameters are unknown, and you have to kind of set those up or make your best guess for what the parameters are for the model. Okay, and you can use an error cost function, and what this is going to do is kind of minimize the error function, give you the smallest error, or the minimal deviance from the actual values. Okay, so that's one way you can kind of check for the best model, or the model with the best parameters. Okay, there's some different distributions, and we'll use some of these in the modeling today. You can look at interval, Poisson, gamma, uh, Bernoulli, which is a binary target, and then entropy, which is a proportional target. So the error function's a little technical over here, but we'll try some of these different methods. Whether we're looking at intervals, counts, amounts, binary, um, one or zero, or if it's a proportion that you're looking for. All right, so there's different activation error functions that we're going to look at in these combinations. So we might be looking at a log function, a logit function, and the activation function based on the link function is kind of how we set it up. So we've tried a lot of these in separate form. We'll kind of combine some of these link functions, activation functions, and error functions in the same network, looking at some target. Okay, logistic, we've done that before. Exponential, um, a lot of these distributions. You know what normal distribution is, and so we'll look at some of these options when we set up the activation and error function. Okay, robust networks. Optimization methods. Okay, so you can set up your network by going either forward or backward. So you can kind of add uh, pieces until it gets minimized, or you can start at the end and kind of go backwards and then take away weights that way. So kind of like the same idea, although slightly more complicated, but the same idea as when we started with a big linear function in um,
Like a
MDA504.
jump, isn't it?
I'm sorry, what's that, Omer?
Like what we did in jump in the first
Yeah,
MDA502.
yeah, that's correct. That's
Yeah.
exactly what I was going to say. Yeah, so you're ahead of me there. So I was going to say exactly what Omer said is that we're using jump, and we have a big function with a bunch of variables. And there are two ways to approach it. Either start with one and keep adding them until it gets better, or start with them all and start taking them away. So either way should get you to where you want to go. But yeah, that's exactly the idea. Right. Okay. So we'll revisit the sigmoid function that we used last time and a couple times in Enterprise Miner, the last session in 503. Okay, and you can have some type of iterative updating, and when you initialize the weight vector to some random value, and then you set up some optimization method to update the vector until it keeps improving, right? And you can do that with this technique called gradient descent. And there's a couple videos I'm going to show you to watch on your own time there on Blackboard. But this is a nice concept to learn about here in this section. Propagation, which is kind of going the opposite direction. Um, and so we'll look at those things. Okay, you can add the update vector to the weight values from the previous iteration to get new estimates, and then if no convergence is achieved, then go back to step 2. So you kind of set it up where it keeps improving based on some criterion. If it doesn't converge or doesn't agree upon a model, you can kind of go back to step 2. All right. So backpropagation, you can start with some error function and try to get it uh, minimized by going like backpropagate until it gets until the error function gets minimized, and you can iterate until you get convergence. So you get the new gradients, the new values, and then once you get the correct new values, you can plug them in, recalculate the error function, and see if it improves. All right, and there's a lot of chain rule going on that you probably learned in um, calculus, and so this chain rule in the context of this model or this technique will be is clearly explained in the some of the videos that are posted. Okay, so here's using the chain rule, but little technical here, but you're basically taking the derivative based on all the factors separately. Okay, so partial derivatives. All right, so digit classification. Um, so you can see that gets complicated if you do it in matrix form, and so the nice thing about these networks and enterprise miners, it can kind of do this. It can do a simple technique, but do it for lots of inputs. So here we have 784 inputs and 10 outputs, okay, which comes out to about 13,000 parameters with different weights and biases. And the model can, the way you set it up, optimize the efficiency of the model by kind of applying the same technique for the whole data set, and that way you don't have to do it individually. Okay, training tracks. Okay, so we'll use this code into today's exercise, I believe, or the next one. And so this is the neural procedure, which sets up the neural network, and you can construct a custom feed-forward network. And so that way, your network can learn, and based on new data, it'll use the learning procedure it acquired from the previous analysis or data crunching, and then use that to make decisions based on what happened and how it learned. Okay, this code converts the specified data into a data mining database and catalogs it. So uh, it can specify, it can kind of break the data into separate databases and catalog it based on where it thinks, like it's kind of like grouping. Okay, this code defining the architecture. So this is used to define a network with at most one hidden layer, and it's the simplest way to define an architecture. So this will set up or define the architecture for your model by running this code. Okay, another way to define the architecture is use the connect code, and this enables you to define any feed forward neural network architecture. Okay, and so you connect or use the connect code that's provided, and then if you run that in enterprise miner, it'll define it as a feed forward, like you keep adding portions into your neural network and build the architecture. Okay. Uh, okay. So sequential network construction, or setting up multiple networks at once. So how many hidden units are required to fit the data? And so the idea is that you want to have enough hidden units, but not too many because it complicates the situation. So you can build the hidden layer one at a time, and then the network is implemented as follows. So you follow these steps. So you create and train a network consisting of an input layer, another hidden layer, and then a single unit, and then an output layer. So you always have in these networks input layers, hidden layers, and outputs. Okay, and you connect them in a network. Step two is you can freeze the weights, okay, except for the bias term. All right, and then oh, okay, and then run again. And step three is you add a new hidden network connected to all the inputs and outputs, but not the other hidden units, and retrain and see if your model learns anything. Okay, then unfreeze and go again, uh, and all the weights are updated if it improves the model. Okay, and you determine the change in goodness of fit, or like the lower error, the better model, after the hidden unit was added and updated. Okay, if it degenerates or gets worse, then you remove the last hidden layer, and retrain it and stop. Otherwise, if it's getting better, go to step two again and keep improving. Okay, so sequential network construction is exactly what it sounds like. It's instead of having one network like this number one here, you have multiple networks in sequence. So there's, in this case, there's six sequential networks going together, and the red portion is the training portion. And so basically, like you can freeze this part of the network, and then train the rest, and then unfreeze it and update. Okay, so you complicate the calculations. I mean, sorry, you simplify the calculations by freezing, then updating only a certain portion. In this case, the blue portion, and then unfreeze and update again. Okay. Um, so additive models. So in this type of model, or a generalized additive model, the targets is expressed or given as the sum of the individual nonlinear univariate functions. And each of these univariate functions is essentially the effect of the corresponding unit holding the other inputs constant. So it's the partial derivative of one thing of the function with respect to one variable, holding all the other variables constant. So that's the concept of the partial derivative. And this might not perform well if there's strong input interactions or strong, uh, what was it, like multicollinearity, if the variables are related. Okay, so here we have a additive neural network in which, using this procedure, you set up a neural network that learns and makes um, decisions when new inputs go into the learning process. Okay, so input layer, hidden layer, output layer. Okay, another methodology is this GANN, or acronym GAN methodology, where you start with a linear model, you fit um, 4 degrees of freedom at least, and you look at the partial residual plots and see if those what the correlations are, and you can add or prune. You could add more, in this case going from 4 to 7, or you can take away if that improves the network. And so pruning means, or so adding means like add um, a node here, like this is, if you add this one, then you're adding. And pruning means like cut off this, like if you took this away, that's pruning. If you add a layer, that's adding. Okay. Uh, Okay, you can have a consolidation layer where again that we're looking at a graphic of the input layer, the hidden layer, and the output layer. So you can look at the partial residual plot and prune each input if it's not adding to the model. Okay, so similar, it's a modification of the previous the GON architecture, adding linear layers to consolidate the output from the hidden layer for each input. So it's similar to the previous one, but a little bit, just a little tweak on that. Okay, partial residuals. Looking at the residuals, well, it says here the partial residuals are the difference between the target variable and the part of the additive model that doesn't include the input under investigation. So you're looking at just uh, a correlation between two variables, just say like y and x, and the partial residual is the difference between the target variable and the part of the model that doesn't include the other input under investigation. So just the residual associated with that those two variables. Okay, and then the gradient descent method is also explained very nicely in a couple videos they're posted on Blackboard, and I'll show you those. You can take a look at that concept in more detail after this. Okay, so what you want to do is outline the three variants of gradient descent. So there's batch gradient, stochastic gradient, and mini batch gradient. And you can illustrate the difference here. So batch gradient kind of does the whole batch. Uh, stochastic takes samples and learns from the samples. And mini batch just takes a portion of the whole data set. Okay, so here's a depiction here, and here's the code, and here's the depiction. So you're using all the training observations to get the gradient descent. Um, and so you're trying to result here in a smooth error minimum, or minimize the error. See how it gets down to a point and just stop the error point, or the error minimizes and doesn't change. Okay, so you want to get the error minimized, and then when you take more steps, it doesn't change. Okay, this is stochastic gradient descent, in which you use just a training observations to get an approximation. Essentially, you'd want to use this method if there's way too many, if you have thousands of observations. Doing this would take a long time and might even lead to computational, like it just might take way too long to computate. And so what you can do is get uh, training observations that get the approximate um, results, and then use that as an approximation of the rest of the model. Okay, and this one, okay, this one you divide the whole training set into different batches. So you use a subset of the training observations to get approximations or approximate gradients on each iteration. And this is less erratic because you're using a simpler procedure to the error minimum. But if you have lots and lots of observations, you might want to use this one because this minimizes the computational um, ability of the whole method. Okay, so three types of gradient descent options. Okay, time series, and we'll start this technique in this lecture and in these examples and the homeworks, then we'll continue on. But time series is when you're looking at the prediction of outcomes that are measured at points of time, and so you can use time series to make a forecasting prediction, uh, model the past, or characterize the past. And so you can use a couple different components to set up your time series model. So the autoregressive or AR component, oh, Okay, so the autoregressive component, this predicts the current values of the series um, with a constant and a combination of a weighted average of the previous observations or lag values. So this basically predicts the future or the next observation with what's happened in the lag values. So like if you're looking at uh, I don't know, like a stock price, your prediction for the next stock price would be the previous stock prices, like last month or the month before, something like that. So use what happened in the lag variables to make predictions of what's going forward. Okay, and then the moving average takes the errors and gives some weighted average of those errors, and so the prediction would be based on some weighted average or some weighted, yeah, weighted average of the previous errors. So like a moving average of 4 would take the average of the last 4 errors, basically. So different methods in which you can use individually or in combination to set up a time series model. Okay, so normally in just simple time series, you have just one variable that changes over time, but you can also look at vector autoregression, which is looking at two time series at the same time. So here we have two exchange rates, and you're looking at the time series of this one, and also the time series of this other exchange rate, and looking at how those changes are related over time. So different variables, but the same time period, 1990 to 1999. Okay, and we can set up time delay neural networks. Um, and if you set s- successive values of a time series as targets and the lag values as inputs, okay, you can combine those two components we talked about here, autoregressive AR and moving average MA, and set up what's called the ARMA. You're just combining the two models together as one big acronym. So this is autoregressive moving average, and you can use this as a prediction in your neural network. So a lot of things going on. We're using two classic models or predictors of time series models and putting those into a neural network that learns based on what's happened in the past to both the errors, the the lag components of the data, and the errors. Okay, so see how this is a weight of what's happened in the past plus some error. Okay, a time delay neural network, whereas you're looking at time lagged inputs into a multi-layer neural network to produce a nonlinear autoregression models. And so these are time delay neural networks where you're setting up the two portions where you have the autoregressive part, which is the lag values. So uh, the time series variable 1 year ago or one period ago, 2 periods ago, 3 periods ago, and so on, and also the weighted errors as the moving average portion. Okay, so a couple types of early recurrent networks set up by the Jordan network in '86 and the Elman network in 1990. And so you can this network models only the autoregressive component of the ARMA model, so only this part, the AR. It doesn't achieve the accuracy by including the other components. So you can look at it's simpler to calculate and understand, but if you only use one portion, you might lose out what's being added in the moving average portion. Okay, so you can also implement the moving average component to use a recurrent network in which the network's output is fed back into an input in the next iteration, and this will give the neural network a memory based on what's happened in the past of the lag values and the moving average or errors in the past. Okay, back propagation through time. And so you start unfolding the recurrent network, and this is like reproducing the hidden layers, the layer weight, k times, where this is the number of steps, and then each of the hidden layers gets two input vectors, the original one, and then the output vector that's achieved from the previous hidden layer. Okay, and then you use the input and the context vectors to uh, forward this through the network and get the error, and then you can use the error to go back and apply it to the unfolded network. So you're kind of tweaking it to get what the error would be, and then go back and use it. Okay. So auto neural nodes can be used to construct another type of neural network. So you have multiple hidden layers. Add them one at a time. You set up a training set to perform, and then the activation functions are tried, and it trains or learns, um, and initializes to either uh, give the current weights or change them. Um, and you want to search for the best network until it converges. And this is like a step-by-step process. You have control over the target layer and the error function. You can choose from the training actions here, so you can train. You can select the functions. So we're going to try these three methods and compare them in one of the homework assignments. You can select the functions that are trained until stopping. Okay, so they train until they learn when to stop. Increments, or you go incremental, and those are added one at a time, and it only retains the layer if it lowers the average error. Otherwise, it doesn't, because adding it didn't improve the model. Or search method is you can look at nodes are added according to some predetermined architecture, and the best network is retained, which is the default. So this is the default, which we'll try, but we'll also look at increment and train. Okay, we'll look at single layers, block layers, funnel layers, and cascade layers in the context of these following training options or training action options. Okay, modifying the tolerance. The tolerance configures the search, and so low would be there's no search. Medium, the default, you perform some search, and high performs a very uh, very extravagant search. So different. So no search, default, some search, and then the high performs the training and applies it to the whole criterion. Uh, the training determines when one of the following occurs. So either you overfit and you stop because you overfit, and adding more isn't improving. Uh, Max training time has elapsed. You said train for this amount of time and then stop, or you got to some error, and once you got over that or below that point, there's no reason to continue. Okay, so we'll look at these layers in the context of these training methods or training actions. Okay, single layer, block layer. See how they're blocked? So here's individual, single layer. There's blocks here. Funnel layers where they're kind of the funnels get smaller as you continue, and then cascade where they kind of set up like a cascade waterfall where you got like this one here and then this one here. So four different architecture types that we can set up and try. Okay, so the cascade type is where each hidden layer is connected to all the preceding unit input and hidden units in a cascade fashion. Cascade because it looks kind of like a cascade, right? Um, and it constructs one hidden unit at a time. And so what goes on here is you fit a generalized linear model, you add a hidden unit and connect it to the previous units, and this turns all the previous hidden units into inputs to the new hidden unit. Then you freeze it, and all the weights and biases except from the old output biases, or you train those. Then you unfreeze after you do the training. So you unfreeze the parameters and let the weights change again and retrain, and you keep doing this, and this will integrate the new hidden units weights with the rest of the network. So if you haven't converged, then you got to do it again and wait to or run the system again from 2 until it converges. Okay, so different ways in which the neural network can learn by basically simplifying the model by freezing portions of it, training, then unfreezing it with the updates. Okay. Okay. Um, that's that's it for the PowerPoint. Okay, if you go to the study guide section, I put this is for week. This is from last week. I set up a new one for this week. Okay, if you open up the week 2 Word document, it'll look like this. Okay, so we have the assignment, the second homework assignment, which we'll start on in a minute, with 3 problems in the lab notes, and then there's also some code that goes along with it. And so the code is in that folder from last time, and I also put it in text format because some of you were unable to open the SAS file, so it's also in text. Okay, so when we get to the code, I'll tell you which of these texts to use if you're going to copy and paste it. Otherwise, you can use the code in the folder from last time, which was here. Okay, so this SAS programs week 1 and 2 has all the code in SAS files form that you need for this week and last week. Or I put it in text format that you can copy and paste if this doesn't work for you. Okay. Okay. Let's go. Actually, let's go ahead and then fire up.
Professor, I didn't find this. Sorry, I didn't find this
Oh,
Word file. Where is it?
okay. So this one. Oh, this
Yes.
the okay. So go on Blackboard and go down
Okay.
to study guides.
Okay. Study guide. Okay.
And here's the one we did last week with week 1 document and the code, and week 2 Word document right here. Do you see that?
Yes. Yes. Okay. Okay. Thank
Yeah.
you. Thank you.
Yeah. Yeah. Okay. So we'll start with, and this assignment will be due next Monday via email. So we'll have 3 different questions and 3 different SPK files. So the first one, we're going to learn about early stopping, and these are lab notes 65 to 72. Okay, so if you open up the lab notes, which are, I think, near course syllabus, yeah, open up lab notes, and you'll find, is this it? Yeah, so we'll start with the early stopping um, exercise. So on page 65, we'll start here, and you can refer to that. I printed it out so I can show you the enterprise monitor. It's easier to see. But we'll start with this one. And this is if you have that big file of the SAS files, this is the code we're going to use. But again, I also put it in a text file so you just copy and paste it if you want to do it that way. But let's, okay, so we'll start with this. All right, let me go ahead and get Enterprise Miner up. Okay, so let's go ahead and start with the first one and get some more practice with Enterprise Miner. And the first one we're going to do is again the early stopping exercise on page 65 in the lab notes. Okay, so this will set up the early stopping process, which is one of the easiest ways to build a successful neural network with no parameter tuning. So you can be one of the first approaches that you consider because it's one of the simplest. And so let's revisit or look or use this banking data set, which has 2,000 customers, okay, who had an opportunity to acquire a new investment product. And so the variables are this one, which is did they acquire it, yes or no, which is just binary. The average daily balance in the checking account, the number of ATM transactions per month, the length of time of their current residence or house, the total amount of checking deposits, total amount of checking transactions, monthly income, amount of investments, and savings account balance. So the target is did they acquire the banking product or not, given these inputs. Okay, and like it says here, an equal number of responders and non-responders are in the sample, but it says it's only essentially 4% of the population. So unless the observations are to be ranked, then we have to make a prior probability adjustment to make sure we don't bias this information because it's only 4% of the population. So we'll make a little tweak when we're uploading the data. Okay, so we'll start here, and I'll go ahead and switch over to Enterprise Miner and kind of go with we can do it together. Okay, let's set up a new project. So let's do File, New Project. Next. Okay, and I called this one the name of the data set, which was banking. I think I'm going to call it, so you can call it banking, B-A-N-K-I-N-G for the data set. I'm going to call it banking 2 because I think I already have another banking one from doing this before. So you can call it banking or some version of banking. Browse. Okay, choose your folder in the E drive. Okay, so banking in your E drive folder. Then next, next, finish. Okay, let's create a new diagram. So file, new diagram. And let's enter early stopping as the diagram name. All right, hit OK. Okay, then let's open a new data source and get to the banking data set. So File, New, File new data source. Then Next, then Browse, and you want to go in the DMNN41 library and open up the banking one, this one, and hit OK. Okay, next. So you should see that there's 9 variables that we discussed and 2,000 total observations. All right, so next, advanced, next. Okay, let's change the role of acquire to target because that's our target. Did they get the product or not? So the role of acquire is now target, and that's all you want to change there. Okay, next. Okay, so now we're going to make some quick adjustments based on the fact that only 4% of the population responded. So hit the where it says decision processing, hit the yes button, and then next. Okay, and then the prior probabilities tab, and then hit the yes button here. So do you want to enter new prior probabilities? Hit yes. Okay,
I'm sorry, Professor, can you go back one step?
yeah. Let's go back. Okay.
Oh, yeah.
Okay. Oh, did I? Okay, so then what did I do here? So acquire is target, right? Next. And we do want to do decision processing, so hit this little yes button and hit next. And then when you're here, click on the little tab that says prior probabilities,
Okay, got it.
and then hit the yes button where it says, do you want to enter new prior probabilities? You do, so you want to hit yes. Okay.
Mhm.
Okay, and let's enter 0.04 for the adjusted value of level 1.
0.04.
Yeah, that's correct. So for level 1, the adjusted prior is now 0.04, representing that only 40%, or sorry, 4% responded, and then level 0 is 0.96 for 96%. So this one is 0.04, and this one is 0.96. Okay, so those should obviously sum to 1. Okay, then let's click the decision weights tab, this one. Okay, and then let's click, or what do we want to do here? We want to do, okay. So we just want to see the defaults that we're going to change. And so now click the decisions tab, this one, and there's a button it's not going to do anything or visually, but it'll do something. Click on the button that says default with inverse prior weights. So just click this button, all right? Hit that, it'll do something. Okay, and then click the decision weights tab again to see how it changed from the previous time. So when you hit this and then hit decision weights, you should see these changes. So just double check that your screen looks similar. So this one under level 1 should be 25 and 0. And this one under level 2 should be 0 and 1.041666 repeating. So you should see those exact, yeah?
Yeah, Professor, can you go back to the prior probabilities?
Sure.
Yeah.
Okay, so we're here, and what you did in this point is hit yes here, right? And then you changed under level 1, the adjusted prior to 0.04, and you changed under level 0, the adjusted prior to 0.96. Okay, and then you click on that.
Yeah, got it.
Okay, and then you want to go to decisions. And when you get to decisions, hit this button. And to confirm, we're at the same step as click on decision weights, and you should see these values here that were adjusted from the default. Okay, so everybody good so far?
Yes.
Yes.
All right, so we've set this up to account for the fact that only 4% responded of the population. So once you got these numbers here, just click next, I think 3 times, and then finish. So next, 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 finish. All right, let's drop and drag our banking data set onto the diagram space. Okay, let's add a data partition node, which is, where's that? The sample tab, data partition. Put that down there and connect your banking data set to the data partition node like that. So that's what we got here. Okay, so in the data partition properties, let's change the to 70% for training and 30% for validation and 0% for tests right here. Okay, so under data partition, data set allegations in the properties, sorry, data set allocations, training is 70, validation is 30, and test is 0. Okay. Now let's, under the utilities tab, let's add an SAS code node. So utility tab, SAS code node, and connect data partition to that. So banking to data partition to SAS code. Okay, and you can click on the SAS code node, or it's probably already clicked, but then click on the ellipsis next to code editor over here. So SAS code editor, click on this button. Okay, so it should be in the training code default. So we're in the training code. Just make sure that. And then down here in the empty training code white space, there's 2 ways to do this. So first is right click, open, and you want to choose this file What's it called? Okay, it's called, if you're doing the SAS file that you got from the program files for weeks 1 and 2, so you want C3S1D1 is the SAS code. C3S1D1, SAS file, and hit OK, or hit open. So the SAS file is all right. So on Blackboard, under weekly module, under week 1, under hybrid online, if you downloaded this last week, the SAS programs, that file should be in there. Okay, so the file that I just showed you, C3 S1D1, or if you had problems opening the SAS code, then you can do what you did last time and go to study guides on Blackboard that is set up down here. And then under week 2, you can use this code for the banking. So click on assignment 2 banking code text. All right, and what you have to do is just copy and paste it into the code window like you did last time. So you can either open the SAS file, or you can copy and paste the code into the window. But just make sure the code says program C3S1D1.
Okay.
Okay, so C3S1D1, like I said, either open the file as a SAS file or copy and paste that code from the text file. Okay, and you should get this little code section here in the training code. All right, so everybody got that?
Yes.
Good. Okay, so if you've got the code here, let's hit the save button. And let's close that. And let's run the code. So just right click SAS code node, run, yes. Okay, so when that's done running, you can open up the right click it and results. Okay, and let's go to line 25 to see how many hidden layers, or the estimated number of hidden units should be 3. So double check that you got where it says estimated number of hidden units, any results. You should get 3 there, and that should. Okay, so everybody got that?
Yes.
Okay, let's close the results. Okay, let's go to the model tab up here. And let's add a neural network node, so model tab, neural network like that. And let's connect the data partition node to the neural network, kind of like, so it should look kind of like this. Okay, then with neural network node added, you can click the ellipsis next to the optimization field here. So neural network and right there, optimization, click on that. Okay, and let's change the training technique property, the very first property, to DBL dog, right there, double dog leg. So training technique is DBL dog. So this is a technique, it says in the lab notes, that does gradual improvements over many steps and takes a lot of time to converge. So it takes a step and keeps improving with small steps instead of just converging quickly. So that's what you're doing here. Okay, so training technique DBL dog, hit OK. And let's run the diagram from the neural network. So right click neural network and run. Okay, so once you get that, you can get the results. Right click neural network and results. Okay, you can look at the iteration plot, this one. Under results, iteration plot, you can maximize that. And we can change the option for the plot. See up here where the options of the drop-down menu, change that to average profit. There it is, average profit. Okay, so the blue line is the training average profit, and the red line is the validation. All right, and you can see it stops here at about 34 iterations and converges there. Okay, let's minimize this. Oops, minimize this. And let's maximize the iteration plot. I'm sorry, the fit statistics. This one. Okay, so they wanted you to see the average squared error, which should be about 14%. So let's double check your results. So where it says statistics label, average squared error right there should be about a little less than 14% for the validation. And the misclassification rate should be about 35% right there. Yeah, so just give a look and see if those are the same things you got. Okay.
Okay.
Yeah, minimize this, close the results. Okay, so now we're going to put in a test data set that's set up for the banking and see how the network or the model performs on the test data. So let's see if it holds up with the test data. And what you want to do, up here where it says, like up at the very top, see where the mouse is, where the data is, data sources, right click data sources, and let's do create data source. Okay, we're just going to add in a test data set to test it. So next, browse. And then under the same library, the DMNN41, open up the test banking, this one. Hit OK. Next, and you should see that you got the same thing, 9 variables, but only 1,000 observations. Okay, then next, leave it as basic, hit next. And we don't need a target because this is just the test data, so next. Next again. And what you want to do here, the only change is you want to change where it says step 7, data source attributes, change the role of this data set to test, because it's test data. Okay, so the role of this data set is test, and next. And finish. Okay, now you should have a new data source up here. Let's get that test banking data source and throw it down here on the modeling space. And we're going to connect it behind the neural network like this. So you can put it around there and then connect this, goes into the neural network. So should your flow chart should look something like this. Okay, and then we need a model comparison node under assess, I think. Yeah. Model comparison. Put that down there. And let's connect the neural network to the model comparison node. So it should look like this. Banking goes to data partition, goes to SAS code. And then test banking goes to neural network, goes to model comparison, and make sure this connection between data partition and neural network is set up like you see here. Okay, let's run the model comparison node. So right click the model comparison node and do run. And yes. Okay, and then right click after it's done running, get the results, right click results. Okay, let's maximize the output window under results. Okay, and you want to see that the average squared error should be about 11%. Let's see if I can find that. if you scroll down the line 165, your average squared error for the test data should have come out to 11%. And the misclassification rate, double check that is about 32%. There we go. So we should get those things there on lines.
On lines, yes. Which lines?
165 is 0.11 for 11%, and line 180 is 0.32 for 32%.
Correct.
Yeah. Okay, so we got that. All right, let's close the results. Okay, so we've completed the first question. And so what you want to do is, if you made it this far, you want to save it as a SAS file. So first, you can right-click the model comparison node and do create model package. And you can give the model package name the same format as I said last time, which this one would be first name, last name, assignment number 2, banking. Okay, so you can type that in or copy and paste it and just put in your name. Okay, so mine would be like that. First name, last name, assignment 2, banking. Okay. Okay, and so assuming the model package is set up, just right click it, the title under model package, save as, and you can save it somewhere is the only option is SPK, hopefully. And then that's the file you're going to go ahead and submit for this question. Okay, so first name, last name, assignment number 2, banking, and it should come out to a .spk file. And I'll just save it somewhere for now. Okay, so for this one, number 1, that's the file that you just finished that you're going to turn in for that one via email. All right. Okay. All right. Ready for number 2?
Yes.
Okay. Okay. Number 2 is we're going to do we're going to implement a time delay neural network. So we're going to use some aspects of time series analysis to set up a neural network, and this is going to be on pages 138 to 147 in the lab notes. Okay, so here we go, page 138 in the lab notes, and there's 3 code files or SAS code files. So when we get to it, you're going to either use the code for C5, S1D1A, B, and C, respectively, for the three different choices, or you'll use the code that I posted in text format under study guides, which is for the wine code A, code B, and code C. So the three code files are either in this file that you downloaded, SAS programs week 1 and 2, or they are on Blackboard in text format. Okay, under study guides, and then here's the first one will be assignment 2 wine code A. The second one will be assignment 2 wine code B, and you can copy and paste from those ones. Yeah. Okay. Okay. So what we're gonna do here is we're gonna do a time delay neural network, set it up, and look at a Box-Jenkins wine time series data set that has information about consumption levels of red and white wine in Australia from 1980 January to December 1994. And the variables, there's only a few. The date, okay, the current time period and when it occurred. Red is the amount of red wine consumed, and white is the amount of white wine consumed. So we have dates, we have two time series, both of which we're going to put as targets. Okay, so I'll start here and jump over to Enterprise Monitor, and let's set up a new, uh, what's it called?
New project?
Yeah, thank you. Yeah, new project, exactly. Okay, so this one you can just you don't have to close out, but let's go ahead and start a new project. So this one's done, and then we can do File, New Project. Okay, next. All right, this one again, if you want, you can call it the data set, which is wine. Okay, I believe I already have a project with this name, so I'm going to call this one wine 2, but either one of those is fine. And then just choose your folder. Okay, so wine or wine 2 under E drive folder, and then next, next, and finish. Okay, let's set up a new diagram. So file new diagram, and if you want to go according to the lab notes, you can call this TDNN, which is time delay neural network. So you can call this diagram TDNN for time delay neural network and hit OK. All right, let's open the wine data set. So File, New Data Source. Next, Browse. And I think it's in the same library, so DMNN41, you want to choose the wine data set, which is the very last one, alphabetical order. Wine, okay. And next, should see that there's three variables that we define, the two types of wine and then the date, and then also there's 180 observations for each, or total. Next, And basic is good. Next. So now we want to change the role of date to time ID because that's just the date. So date role is under time series. You can set that as time ID. And let's change the role of both red and white to target. Oops. Okay, so we have two targets, red and white, and the role of date is time ID. That's not going to affect anything. That's just the date of the observation. The role of red is target, and the role of white is target. So these change all three under role to time ID, target, target. Okay, so we're gonna have two time series models at once, one for red and one for white, and we can compare them. All right, and then next, 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 finish. Oops. Okay, then let's drag the wine data set onto the space. Okay, let's add a SAS code node to the model from utility tab, SAS code. Drag it down there and connect it. Okay, so one data set goes to the SAS code node. All right, so here's the part where we're going to put in the code. So you're either going to open the SAS file that I specify, or you're going to copy and paste it from here. All right, so click on the SAS code node, and under code editor, click on the little ellipsis and open that up. Okay, and under training code, which should be the default, you want to right click down here. If you're doing the opening, right click the blank white space under training code and do open. And the file you want to choose, if you have it saved, is C5S1D1A. Okay, so C5S1D1A and hit open. And it's a pretty simple code pretty simple lines of code. So either open it or it should be this one, assignment 1, assignment 2, wine code A, which should give you the text file that you can copy and paste. But just make sure it's this one, C5S1D1A. Okay. So C5S1D1A, either open the SAS file or copy and paste it there. Either way, it should work. Save that. Close it. Okay, so that first code is going to make sure that there's a normal distribution for the two time series. Okay. Let's rename this file, this code file, because we're going to have multiples. So right-click the SAS code node, rename, and let's call it univariate. Okay, univariate. You can see that. And hit OK. So this is the code for univariate. And let's run that let's run the code. So wine goes into the univariate code and right click, run, yes. Okay, and then let's get the results. Right click, results. Okay, and let's look at, we want to look at the test of normality for both the red and white. So if you start, 56. So the first group of stuff is for the red wine. All right, so we're starting here with red. If you scroll down to line 56, around there, what they're showing you here is that the tests for normality are rejected because your p-values are not uh, less than 0.01. Okay, so what we see here is the red data set, or the red time series, isn't, we can't confirm that it's normally distributed, and the same is going to be true for the white if you scroll down to 133. Okay, right here we're starting the white wine, and this test also shows that the p-values are a little bit higher than we'd like. You can see the low test statistics, which would essentially mean that it's close, but we can't confirm that both of these time series have a normal distribution.
Professor, can I have a question here, please?
Yeah.
There's a for tests for normality.
Uh-huh.
Okay, and the p-values, the first line is PR less than W less than
Yeah.
0.00. What does it mean?
Oh, so remember these are just the p-values for so this is like, there's 3 different tests for normality. This one, the Shapiro-Wilkins, I can't pronounce this, Komarov-Smirnov, and the Kramer-Von Mills, and the Anderson. So these are 3 different types of tests for normality. And so normally for the normality test, you'd want like a test statistic that's over 2-ish, and a p-value that's like essentially 0. And so what we see here is that the test statistics are pretty low, and the p-values aren't, or they're bigger than 0, right? So that would say that the test statistics aren't low enough, and the p-values aren't. I mean, sorry, the test statistics aren't high enough, and the p-values aren't low enough to reject the hypothesis, right?
So there is no, for example, for the Shapiro-Wilk, what is the p-value?
0.001.
Okay. So null hypothesis rejected.
Right.
Okay. Thank you.
Yeah, you're welcome. Yeah, that's right. Okay. So we've confirmed that, or we've determined that we can't decide, or we can't confirm that both the red wine and the white wine are normally distributed. So we're gonna have to do something about that. Okay. So let's close this.
Professor, could you please repeat after the code file step?
After which step?
Like where we have pasted the code under the SAS code?
Yeah. So let's. Okay. So you. Okay, so for the univariate, you put the code in, right? Oops. Okay.
Before univariate. Yeah.
Okay, before, yeah, so you have, this was SAS code,
Yeah.
and you clicked on the code editor ellipsis here.
Mhm. Okay.
All right, and what we did here is under training code, you open the SAS file for C5S1D1A
Mm-hmm.
right there, or you can copy and paste it from this file. Oops.
Okay.
Okay, so assignment 2, under study guides down here on Blackboard, and under week 2, here's the one, assignment number 2, wine code A text. All right, that's also the text file for C5S1D1A. So either open the SAS file or copy and paste the code.
Okay.
Okay, and you got this code here in the training code.
Yes.
Okay, then save that and close it. And then what we did is just rename it univariate, like right click, rename, and you can call it univariate. And then we just ran it.
Okay, got it.
Okay. Okay. Now I think we're on step. I think we're on step 23. So that's where we'll continue, right? Okay. Step 23. So let's add another SAS code from the utility tab and connect it here. So utility, SAS code, you can throw it down there and connect it to the wine data set. And for SAS code 2 node, let's click on the code editor, ellipsis here. Okay, so we're going to open another code under training code. So right here where it says training code in the blank space, there's nothing there yet, which is why we need the code. So right click that area, open, and you want to navigate to the file C5S1D1B.SAS if you have that. C5S1D1B, open, and save it. Or the other option is under study guides. You can get the same code in this title. Assignment number 2, wine code B, should give you that same code. Program C5S1D1B, and you can copy and paste that if that's the method you're going with. Okay, so this says it's going to generate time lags and also going to log it. So if you look somewhere in here, it should, because we determined that the data was not normally distributed, we're going to take time lags and we're going to log transform those. Okay? So you got your code here and you save it. So we're trying to fix for the non-normality thing in both time series. Close. All right, let's rename this one SAS code 2, right click, rename, and we can call this tap delay.
Tab delay.
Yeah, so TAP delay, tap delay, and it's like it's the first line of code in that. Okay, so tap delay, okay. Um, let's run that. Okay, wine goes to tap delay, right click, run. Yes. Okay, now let's add a neural network from the model. So just wait till that, you don't need to open the results yet. Just run the tap delay and then under model tab, neural network, this one. And I'm gonna just, because the picture on page 140 is a little bit different, it doesn't make a difference, but I'm just gonna make it so it looks like the diagram on that page. Is just, if you flip these around, you do that. Okay, so wine goes to univariate code, and then wine goes to tap delay, and then tap delay goes to neural network. Okay, then for neural network, um, the properties next to variables. Oh,
Professor,
yeah,
if you don't mind,
yeah,
tab delay will be go to neural network and univariate as it univariate. There is nothing.
that's correct. Yeah.
Okay, okay.
Yeah, all right. So click on the neural network node, and over here, under properties, the ellipsis next to variables, open that. Okay, so it just wants you to see what it created with the code. So basically, there's the red, there's 12 lag values, like the last period, 2 periods ago, and all the way back to 12 periods ago. And the same for white. I don't know why they're in like weird order because the ones go first, but uh, there's R1 to R12, so 12 lag values of the red wine, and there's W1 to W12, which corresponds to 12 lag values of the white wine. So those were added to the model to fix the non-normality uh, problem. And if you see that is the same, you can close that. Okay, now with neural network still selected, click the little ellipsis next to network under properties, network. And let's change the direct connection to yes, and the number of hidden units to 1. Just type it in. All right, so direct connection is yes, and number of hidden units is reduced to 1. Okay, so this is going to help, the direct connection going to help uh, with non-stationarity. So if the errors are changing over time, hit OK. All right, let's add another SAS code under Utility, SAS code, drag it down. Okay, and let's put this code over here and connect the neural network to that. So we're wind tap delay neural network SAS code 3 going along here. And let's rename this code SAS code 3. Right click, rename. Let's call it plot, like a plot of the data. PLOT. Okay. Okay, and once you do that, with the plot node, click on the little ellipsis next to code editor. Okay, and this is our last code, our last import of code, but under training code, right click the white space, open, and if you can navigate to the files, you want C5 S1D1C .sas, open. Okay, save that. So this is going to create some plots or some graphs for us that are predetermined. And the other code, the last code, is also here under Study Guides, Week 2, Assignment 2, Wine Code C, should also give you a copy and paste option, text file, for C5 S1D1C. All right. Make sure that's saved. You got the code there, C5S1D1C, in the training code area. Save it, close it.
Hi, Professor. When I click on the code editor, it doesn't open and my screen froze. Is there a way to refresh?
Oh yeah, so like sometimes if it does, if you click on the wine data and then go back to the diagram and then click on plot, it should let you redo.
I can't click anything. It's the whole program froze.
Oh, if the whole program froze, you might have to just close it and open it. How far have you gotten?
Just same as you.
Okay. Yeah,
I
it
can
should.
just close it. It'll save.
It'll save whatever it's like got to before it crashed, I think.
Okay.
But if it's frozen, I guess the only option is to close it and open it again.
Okay.
So why don't you try that, and when you get it open again, just do File, uh, Recent Projects, and that one should be there.
Okay.
Okay, and I didn't see the chat, so I already helped you. I already got you caught up on that, right? Tejas Vita, you're that was from before, right? You already got caught up.
Yes, I got
Okay,
it.
okay, great. So sorry, I didn't see
Yeah.
it.
Okay, I just reopened mine. I think it takes some time to load.
Okay.
Okay, I got it. Thank you.
Okay. And then yeah, so just make sure, where are we? Oh,
Just
so
save
just
the code.
yeah, so click on the plot um, one and just click on code editor. And make sure your training code is still there. So make sure you still see the code for C5S1D1C. Okay, you got it? Okay, so I'm gonna close this. And then assuming that the code there, I don't think we did this yet, so let's run, once you get the code into the plot SAS code node, um, let's run that. So right click the plot node and run it, and yes. All right, then let's get the results. So right click plot and results. Okay, let's go down to line 26, and we want to see, which is which here. Yeah, the first one is for the red, I think. So you should get an MAP of 0.517, 0.0517 on line 30, and for the training set and for the validation set on line 38, you should get an MAP of 0.0949. Okay, suggesting that the mean absolute percentage error was very low, like less. There's about 5% here, and about 9% here. And if you look for the white, the line 46, MAP is 0.0423, and the MAP for the validation 0.0724. Okay, so what that's telling you is that the error for the training and validation set for both the red and the white is very low, about 5%, a little less than 10%, so on. So pretty low errors given this all these observations. Okay, and then when you have this the output window open, if you go over to the top up here where it says results node plot diagram TDNN, uh, see the menu up here for view. So let's do view, SAS results, and view SAS results train graphs. Okay, there you go. Here's the data time period. And for red, this is the actual data. And for predicted, you get the red dotted line. So you can see it's pretty close to the uh, historical data. And it looks like we're capturing, like this data is seasonal. So it goes up in certain times and goes down in certain times of the month, and also kind of trends upward. So we're just kind of capturing uh, the main seasonal behavior and the upward trend in our prediction. Oh, whoops. Okay, I didn't mean to close that, but I will. So leave that open if you didn't already close it, or you can do for plot, right click, results, and where we're at. View, SAS results, train graphs. Okay, and then we looked at this one. So if you have this graph pulled up, down at the bottom, there's like a little slideshow. If you hit this arrow, see that at the bottom? So down there, there's like a back button, a play button, a right arrow. If you hit the right arrow like that, it should show the same um, graph for the validation set for the red, so the validating red data and the prediction. Okay, and this one fairly close, but not as close as the other one. We can also look at the white wine. If you hit this button down here again, that'll take you to the training set for white. The black line being the prediction, or the black line being the actual data, and the dotted red line being the prediction, which predicts a lot of the seasonal movement. And then I think hit it one more time, the right arrow. Which should show you the validation data set for the white, the black line, and the prediction, which is the dotted red line that um, goes along with it. Okay, so these models did a pretty good job of predicting the time series data, right? And, okay, so we finished the model for question number 2. So let's, everyone good on this one?
Yes.
Okay. All right, let's save this one. If you go to plot and right click and create model package, let's call this one okay, let's call this your first name, last name, assignment 2 wine. Okay, so something like that. Your name, assignment 2 wine. Okay. All right, and then once that's finished creating, you can right click the title of the model package under model package and save as something the same name in a .spk form. All right, and you can save that, and then you can turn this one in for your question number 2. All right, so we did this one, or we did this one and we did this one. Okay, so we got one more. Okay, so I think the last one is the shortest, but everyone up for one more problem?
I think it's better to finish it and finish the class earlier. This is just suggestion.
What's that?
I think it's better to continue
Yeah.
if the others are okay.
Oh, of course.
Then we can finish the class early.
Yeah, that's exactly what I was thinking. Okay, let's continue.
Okay.
All right, the good news is this one does not have any code that we need to import, so you don't have to worry about that. This one. Okay, number 3, comparing autoneural architecture, and we'll be looking at lab notes 148 to 151. Right, I went too far there. Oh, what was the next? Okay, so we're going to use that same Titanic data set we've used a few times to see the different characteristics or attributes that affect your survival rate, like survive or don't survive. So we'll do an autoneural network with a single layer, a block layer, a funnel layer, cascade layer in the architectures. And we'll use those different training options that we discussed in the PowerPoint. Train 1, increment 2, and search 3, and then compare them on how they perform in the Titanic data set that determines what are your chances of survival based on all these characteristics. Okay, in this one, we're going to set up a new diagram, or actually, we already formatted this data set, which you should have. And so let me see if I can. Okay, so it doesn't give you the options when doing the data because we've already done it before and it's the same. So you should have this data set, assuming you did 503. So if you do File, Open Project, there should be one. I probably have I have like 3 of them. So you should have one for Titanic with the data, like the data options set up correctly. And so just open up, we only want the data, so it doesn't, the model diagram doesn't matter. But go ahead and find your most recent um, project with the Titanic name and open that up. Actually, I'll open mine from, yeah, okay. So everyone should have, hopefully, unless you named it something else, you should have some Titanic data set. And if you do, you can just hit OK and open it. Maybe that didn't work. Um, oh no, it did. Did it? No, it didn't.
So do you open the diagram?
Yeah, well, I really just want the data set. I don't really, let me try again. Let me do File, Open Project. Let me try this one that says Titanic 2. Open. Okay. Yeah, that one has the data set. So hopefully one of your Titanic projects that you did previously, when you open up the data sources, it'll have the Titanic data file that we can use. So does everyone have that?
Yes.
Yes?
Mhm.
Number of observation 1309.
Yes, oh yeah, that's correct. Okay, so if you have a project with Titanic, you should have the data set in there, and it should already be set up um, with the appropriate targets. And so let me know if you don't have that, but we're going to use that data set that we previously set up in 503 to do this analysis. So let's continue with setting up a project. So let's start here. Okay, let's make a new diagram. So File, New Diagram. And let's call this auto neural. All right, so like step 2, auto neural. Yeah, auto neural. All right, so we're setting up an auto neural network. So auto neural is the diagram name. Okay. Okay, and then assuming you have the Titanic data set here, just drag it onto the space. Okay, now we're here on step 4. I'm going to use the restroom real quick, and I'll be right back in like a minute. So just hold on 1 second, and we'll continue with step 4 here.
Awesome. Awesome.
Okay. Okay, step 4. Let's add a neural network node and drag it down here. So model tab, uh, model tab, sorry, model tab. Where is it? Neural network. Oh no. We want auto model tab, auto neural. There we go. Okay, so under model tab, you want the autoneural node. Connect that, and let's connect Titanic to autoneural. Okay, and let's click on the properties. Let's change the train action property to train. So train action right here. See that? Change that to train. So autoneural properties, train action is train. Let's set the maximum iterations property to 50. And okay. And let's set the number of hidden units property to 1. Okay, so with the autoneural node, under properties, we did change the train action property to train. We set the maximum iterations property to 50. And we set the number of hidden units property to 1. Okay. A few more things. Let's change the tolerance value to high. So tolerance is now high. Set the direct property to no. Okay, under activation functions, direct property is no.
It's direct property or
So under properties, where it says direct, like it goes general train activation, like down here where it says activation functions, change the direct option to no. Okay. And let's also set this option under activation functions SINE to no. All right. So we made all these changes here. Steps 6, A, B, C, D, E, F. Okay. Okay. So I think we did that. All right. Now let's right-click the autoneural network and rename it. And let's call it autoneural train. Okay, autoneural train. Okay. Okay, now we're going to do a couple other ones and just do a copy and paste method. So click on this and right-click it for copy, and then click anywhere else on the diagram space and do paste. So we have another autoneural network node. Okay, let's put this one down here. So let's connect them to the data set like this. Oops. Okay, and let's rename the second one. So the first one was autoneural train. The second one we just copied and pasted. Let's right-click it and let's rename it autoneural increment. Autoneural increment, okay. And let's change it to increment. So change the train action to increment. So under this one, autoneural increment, train action is increment. Okay. Now let's copy and paste another autoneural node and set it to the other option. So we have the 3, and we'll double check this in a second, but right click either of these, copy, and paste it somewhere else. And let's connect Titanic to this one. So we have the 3. And this third one, let's right click it, rename. Let's call this autoneural search. Okay. And you can probably guess we're change this one to search. So change the train action to search. Under autoneural search, train action should be search. So let's double check what we got. So this one, if you click on the first one, autoneural train, the train action should be train. You click on this one, autoneural increment, the train action should be increment. And if you click on this one, autoneural search, the train action should be search. So the name should match the train action. See how it's train, increment, search.
Professor, how did you get this autoneural train, the first one tab?
Oh, so the model
Yeah.
tab, it's
Okay.
the first one here,
Oh,
autoneural.
right.
Yes. Yeah.
Okay.
Mhm.
Maybe I missed that. Oh, thank you.
Mhm. Okay. So now let's throw in a model comparison node under assess, model comparison. Put it over here. And let's connect all of the autoneural nodes to the model comparison node, kind of like that. Okay, then let's run this. This might take a few minutes. I can't remember if this one took a while, but model comparison, right click, run, yes. All right, so I think that should mine finish going. Um, now let's get the results. Right click, results. Okay, and then let's open up the output window. Okay, so we're double checking which method performed better. So if you go to line 29, actually I don't think that's the right line. Looks like it's actually around line 60. So we're looking at the search, the train, and the increment, and seeing how they, which one had the lowest misclassification rate, and which one had the lowest average squared error. So you should get that the best one for the lowest misclassification rate, line 67, was for the search 0.19404. And also, even though it's ranked by this, the lowest average squared error is also for the search, which is 0.14523. Okay, so for this one appeared to be the better model here, or just compared to the other two. Okay, so we did it as a single layer, and now we're going to do it as a block layer, a funnel layer, and as a cascade layer. So basically, we're doing those techniques we learned. If I can like. Okay, so yeah, we're using these. So from the PowerPoint lecture, we're using the train, the increment, and the search methods together, and we're applying them all three over these different types of architectures. We just did single layer, and now let's look at the other three. So we're doing exactly what we talked about in this slide and this slide. Oops. Okay, let's close the results here. And let's click on Auto Neural Train. And let's change the architecture property to block layers. Okay, so here's, I think we need to do this. Okay, so Auto Neural Train, let's change the architecture property to block layers. So architecture over in properties right here, change it to block layer, and make the same change for the other ones. So this one, Auto Neural Increment, is also block layers, and this one, Auto Neural Search, is also now block layers. So this one should be block layers train, block layers increment, block layers search. Okay, so let's compare these three methods over the block layer architecture by doing model comparison, right click, run. Yes. Okay, then let's get the results. Okay, if you maximize the output window under results, let's see which one was the better. And if you scroll down to line 67, you should see that the search model, line 67, had the lowest misclassification rate of 0.2204, and also the lowest average squared error of 0.15961. So the search one was the better one, again, for this architecture. Okay, so we got that. Everyone good so far?
Yes.
Yes.
All right, let's try the other two types of architectures, which are funnel and cascade. Close this. Okay, so we're going to now make all the change all the architecture types to funnel and run the node again. So click on the train one, change the architecture. Click on the train one, change the architecture to funnel layers. Increment, change the architecture to funnel layers. Search, change the architecture to funnel layers. All right, so this node, train funnel layers. This node, increment funnel layers. And this node, search funnel layers. And when you make those changes, click on model comparison again and run it. Okay, then we can get the results. Output window. And you scroll down here. Let's double check. And so it looks like on line 67, the search had, again, the lowest misclassification rate, but it looks like this one, the train, had the lowest average squared error. So it's ranked, it's sorted by this by default, but this one actually had a lower average squared error. So this one still seems to be the best so far, but this one did perform better in average squared error wise. See how this one's lower than that? I mean, they're all pretty close. But. Okay, so you should get a misclassification rate on line 67 for the search of 0.19939. Okay, last architecture type. Close this. Oh, no, I don't want to do that. Sorry. Okay, now let's change all the architecture types to cascade, the only other option. So click on the auto neural train and change the architecture to cascade. Change the increment architecture to cascade, and change the search architecture to cascade. So train, cascade, increment, cascade, search, cascade. So just double check that those corresponds to the right train action, search, increment, train, and then they all should be cascade architecture. Okay, model comparison, right click, run. Okay, yeah, this one takes a little while, if I recall, so it's still going. All right, still going, but this is our last step. So okay, there we go. All right, so I'll give everyone a second here. The it should stop running pretty soon.
I think Search is a hero still.
It's still going.
No, the Search.
The what?
Search is still the first one.
Yeah, yeah. Well,
Yeah,
this
that
one,
was
yeah,
good.
this one takes a lot longer. So hopefully it stopped going. And if it did, we can click on model comparison, right click results, and let's see.
Yeah, 0.159.
What?
66 is Search. Search is gonna be
Yeah,
0.159.
yeah.
66. Yeah.
Right. Oh, yeah. This one did way better this time. So, yeah, on line 67, the misclassification rate was the lowest for search by far, and also much better at the lowest the average squared error. So this one looks like in all cases but one, the search had the best both the metrics, right? Okay. That. Okay, we're done. Um, so that everyone good on this one? It finished running? Okay. And if it did, we can right-click Model Comparison, create the last model package under the format first name, last name, Titanic. Okay. Name assignment 2 Titanic. Create the model package. Oh, already have that. How about Titanic 2? All right. And then, oh man, I have a bunch of them over here. Okay, I see why there's, oh, I should have saw that. All right, this one, or whichever one is, I think these are both the same for me, but name assignment 2 Titanic, right click, save it as the SPK file somewhere. Okay, save that, and then that's the file you're gonna email me. All right, everybody good on this?
Yes.
Okay. Almost. Okay. Okay, it looks like 16 people. Is everyone here? How many people are in the? Maybe we might be missing one person, right? Okay, so I'm gonna have to take attendance because it looks like there's one person missing, but let's okay. So turn in these three files for homework 3. And you can email me this one, and this one by next Monday, February 14th. So that's for homework 2, assignment 2. And you can read along independently for your online portion. Um, the T1 textbook, chapters 3.1 to 3.6. Okay, so under course text, here's the T1. All right. So you can read those sections to kind of reinforce what we learned today. And then there are, I think, 4 videos you can take a look at that explain backpropagation and gradient descent. And those videos that you can take a look at in the week are under weekly module, week 2, hybrid online, StatQuest, and here there are the 4 videos there. Okay, so you can take a look at those and do the reading there. And then there's also some, I posted a few things suggested by the other professor that teaches the course. And there's a housing example you can look at. You don't have to turn it in. There's also some videos on neural networks in the zip file. And so under week 2 stuff, I added a few things today that are optional, but you can look at some more resources here if you want to look at those. And there's some quick lecture videos there. But for this week, just turn in these 3 via email, and then do the reading and watch those videos for this week's assignment. And then, assuming there's no announcements, we should meet in our classroom next week at 6 o'clock and be back on campus. Right?
Okay, great.
Okay, now let me just take attendance real quick because.
So, Professor, that means the next week we will meet on campus.
That's correct. Yeah.
Okay, thank you.
Mm-hmm.
Mm-hmm.
Okay. Okay. I can just look at. So you're here. You're probably here. Yep. You're always here. Joanna's probably here. Right. Yep. Eric. Maybe is K Hailey here?
Yes.
Okay. Oh, are you Chris Lee?
Yeah.
Okay, gotcha. I was wondering. Yeah. Okay. Do you go by Chris?
Yes, I do.
Okay, so I'll call you. Okay, Chris. Okay, then you're here. Definitely here. Cute. Yep, here. You're here. That's here. Maybe that. Oh, that both here. You're yeah. Okay, so maybe Zihao Zhang is not here because you're here, and yeah. Okay, so am I correct? Like Zihao Zhang isn't here today? Okay. All right. Well, I will get the video post on YouTube. That if anyone missed it, like you can catch up there. But okay, everyone else is here, and everyone was here in week 1. So thank you for joining. All right, I think that's it for tonight. And just make sure you get the homework assignment from last weekend tonight if you haven't done that. I'll get those grades updated this week. And then the homework 2s are due next Monday, and you got the reading and some videos to watch. And then I should see everyone in our classroom on the syllabus next Monday at 6. So thank you for joining, and I'll see you in a week on campus.
Okay, thank you. Thank you, Professor.
Thank you.
Thank you.
Thank you, Professor. Good night.
You too.
Thank you.